Alright, here we go with the Chapter 2A homework review. This is the first of two assignments for Chapter 2. And this one is a bit more difficult than the first, as you probably found out. So the average this week was lower, but that's normal, so we can't be too worried about that right now. We did have a lot of material in Chapter 2. Most of it was covered on this assignment, and so it did feel a little bit rushed, admittedly. So next week will be better because we have a second assignment on Chapter 2 that'll be due next week. Or the end of this week, I suppose, and that'll give you a chance to review a lot of the important topics from that. But if there's anything on this first assignment that doesn't make sense, hopefully the video will help. If not, if you still have any trouble, please get in touch with me and we'll work things out. Alright, so let's get right into the problems then, and these were mostly identified from Blackboard, looking at the problems we had the most difficulty with. A few of them were suggested by students, so we'll go over those as well. So the first one here is dealing with the relationship between frequency and wavelength. So we're saying that an infrared photon has a frequency of 2,504 gigahertz. What is this wavelength in centimeters? Recall that 1 gigahertz is 10 to the 9th hertz. I didn't format that quite correctly, but that's what it should be, 10 to the 9th. So this is a pretty simple relationship between wavelength and centimeters. I suspect the issue here for most people was units, not the actual math itself. So if you recall, the product of frequency times wavelength is equal to the speed of light c. And in this problem, we're giving you the frequency and asking you to solve for wavelength. So that's all we're going to do is just rearrange this equation and say that wavelength is c divided by nu, the frequency. Now the issue here, though, is we have to make sure that we're using things in the correct units because c is our speed of light constant, which is 3 times 10 to the 8th meters per second. So everything we do in here, we need to have wavelength in meters. That's what we're going to be solving for. And then our frequency nu needs to be in hertz, which is the same as inverse seconds, so seconds minus 1. So here the frequency is given in gigahertz. So the first thing we have to do is convert it. So the frequency in hertz is going to be 2,504 gigahertz times 10 to the 9th hertz per gigahertz. So I believe that should come out to 2.504 times 10 to the 12th hertz. Let me double check that. Yep, did my math right in my head, so that's correct. And then what we're going to do is just plug that into the equation. So lambda is going to be the speed of light, 3 times 10 to the 8th meters per second divided by that frequency, 2.504 times 10 to the 12th hertz. And when we solve, we get 1.198 times 10 to the minus 4, but that's going to be in meters, remember, because these cancel out. This is seconds minus 1, so that cancels out. So that's in meters, and we want the answer in centimeters. So what we're going to do is take that number. We have to remember the conversions here. So 198 times 10 to the minus 4 meters times is 100 centimeters in 1 meter. Alright, so just remember that last conversion because again we're looking for this in centimeters. So always read the question closely because we will, in numerical questions, always specify what unit your answer should be in. So it's going to be 1 times 198 times 10 to the minus second centimeters. Okay, so that was probably the last step that some of you missed, or we just had things in the wrong units in general. So that's how we do that one. Again, just be careful with units and make sure you know how to do exponents in your calculator because those are going to be important in a lot of the problems we do here. Alright, and then the next question deals with photoelectric effect. So as you'll recall, the photoelectric effect, just in concept, is we have a metal surface, we shine photons on it, and in some cases, electrons get ejected from the surface. Now the key part of this is that the electrons only get ejected if the energy of the photon is high enough. If the energy of the photon is too low, nothing happens. When the energy of the photon reaches some threshold value, which we call the threshold energy, with a corresponding threshold frequency. Then from there we can eject photons, and the more energy of the photon that we put in, the faster the electrons that come off. But this one here is just dealing with the concept of threshold energy. So it says the minimum energy needed to eject an electron from a sodium atom is 4.41 times 10 to the minus 19 joules. So that's the minimum energy for a photon that would cause the photoelectric effect in sodium. What is the maximum wavelength in light in nanometers that will show a photoelectric effect with sodium? Alright, so this is basically just using another equation for photon energy that we need to learn. So remember that the energy of a photon is h times the frequency, which can be also written as h times c over lambda, combining it with the equation we learned or used in the last slide. So that's going to be the energy of a photon. So we're given here the energy of the photon, and we want to know what's the corresponding wavelength. So we're going to use this form of the equation, E equals hc over lambda. And we should recognize that energy and wavelength are inversely related. So if this is the minimum energy required to eject an electron, the corresponding wavelength would be the maximum wavelength. The wavelength will need to be smaller than that for the photon to have an energy that's larger than this value. So all we're going to do here is just solve for lambda, which is just going to be when we rearrange hc divided by energy of the photon, and then we just put everything in. So h and c are constants found on your periodic table, so you don't have to memorize them. So h is Planck's constant is 6.626 times 10 to the minus 34 joules seconds. C is 3 times 10 to the 8th, same constant we just used. And then we're going to divide that by the given photon energy that we're going to correlate with the wavelength that we're solving for, 4.419 times 10 to the minus 19 joules. So if you'll give me a second to calculate, I will be right back with the answer. So I don't work these out ahead of time. I do them in real time, which sometimes takes me a little bit of time to calculate, especially since I don't have a calculator with me. I've used my computer. And then we're going to divide that. Oh, come on. I'm going to do something right there. Anyway, we're getting there. Okay, finally, we get 4.51 times 10 to the minus 7. And again, we have to be careful with units because that is one of the answers. But here, this answer that's given is going to be joules cancel out, seconds cancel out. And again, it's always going to be in meters when you first solve for it. So that's the wavelength in meters. But here we're looking for the wavelength in nanometers. We don't want to pick choice B here because that's the wrong units. So we need to multiply this by 10 to the 9th nanometers over 1 meter to convert. So we should get 451 nanometers. So correct choice C is correct when we account for the units that it was asking for. So again, this was a veiled question dealing with just the equation for an energy of a photon. So it wasn't stated directly in that way, but it sort of relates to the photoelectric effect. But the math we're doing is just using that same equation. All right. And then the next one I'll go through here before we get into the Bohr model, which is what we'll cover for most of this review. The next one deals with some concepts with quantum theory, and we want to know which of the following statements is incorrect. So the first is that the energy and position of an electron cannot be determined simultaneously. So this one is true. This is a statement of the Heisenberg uncertainty principle. So there's a mathematical relationship that I introduced for this that we're not really going to use. But again, the concept is that if you're dealing with very tiny particles like electrons, you cannot precisely know where they are and how fast they're moving or their energy, however you want to phrase that, at the same time. So that one's a true statement. That's a statement of Heisenberg uncertainty. B, lower energy orbitals are filled with electrons before higher energy orbitals. So as we got into electron configurations, which was the end of this chapter and will be covered more on the next week's homework assignment, but that was the key concept, that we fill the lowest energy subshells and orbitals first before moving to the higher energy ones. So this one is also true. This is a statement of what we call the Aufbau principle. So all these statements deal with different concepts in quantum theory. This one is the Aufbau principle, and this is the correct way to state that. Choice C, when filling orbitals of equal energy, 2 electrons will occupy the same orbital before filling a new orbital. Now this is the one that ends up being incorrect, because if you recall, when we were filling electrons into orbitals, which we did towards the end of class on Thursday of last week, if we have degenerate orbitals at the same energy, for example, a set of 2p orbitals, when we fill those electrons, we're going to go one at a time first before putting 2 electrons in the same orbital. Okay, so this isn't a statement of, that would be what's referred to as Hund's rule, but this way that we state it is false, because this statement says that we're going to put 2 electrons in the same orbital before filling a new orbital. That's the opposite of what you should do. You should always put 1 electron in every orbital before putting 2 electrons into one orbital. So anyway, this one's false. This one would violate Hund's rule. So it deals with Hund's rule, but it's not stated correctly, basically. All right, so that's going to be our answer, C. Let's make sure that D is also correct. There should only be one incorrect statement here. No 2 electrons can have the same 4 quantum numbers. This is a true statement. This is what we call the Pauli exclusion principle. All right, so it's important to know these different concepts, and some of them are going to come into play when we do electron configurations. Some of them we just want you to understand the concept behind them, like Heisenberg uncertainty, and not really do too much with it, but all of these deal with 4 different concepts in quantum theory. Choice C, which deals with Hund's rule, is the one that is stated incorrectly, so that's going to be our incorrect statement. All right, so that was really the only conceptual question I'll go over today. Seems like we did okay with most of those, but what we're going to cover for a lot of the rest of today are different variations on using the Bohr equation to determine the energy change for electrons in a hydrogen atom, the photons that are absorbed or emitted, wavelengths and frequencies of those photons, and so on. So these all deal with very similar concept and very similar math. It's just what we do with the numbers that we have and sort of just understanding the different variations in these problems that I suspect is what presented a challenge. So we're going to go through a lot of similar problems here, but just looking at the different ways that we can ask the question and how you use the information in the problem to get what you're looking for. Alright, so this first one is that what is the energy in joules of a photon that will cause excitation of a hydrogen atom from the state where n equals 2 to the state where n equals 6? Once you have the answer, determine its log and enter your answer with 3 decimal places. So first, let's just solve the problem itself and then worry about how we're supposed to enter the answer. So again, anytime we're dealing with excitation in a hydrogen atom, electron transitions, all those keywords, we should immediately think of the Bohr equation. Now there's a few different forms of it, but the one that's most useful to us is the one that's in terms of delta E, which is minus 2.18 times 10 to the minus 18 joules. That's the ionization energy of hydrogen. And then it's going to be 1 over the final n value squared minus 1 over the initial n value squared. Where again, these n values are the different quantum numbers that associate with the electron in these different energy levels. So here we're looking for the energy that would cause excitation of hydrogen from n equals 2 to n equals 6. So we're going to put those numbers in to figure out the change in energy of the hydrogen atom or the electron in the hydrogen atom when it goes through that transition. Alright, so we're going to use that constant, and then the final n value is where we end up at. That's going to be 6. So we're going to put 1 over 6 squared, and then the initial n value is 2, so we're going to put 1 over 2 squared for that second term there. And so then we're going to work out the math. Just give me 1 second to do that. And what we come up with for that energy, that delta E, is going to be 4.48 times 10 to the minus 19. And that should be a positive number because what we did was we're going from a lower n value to a higher n value, so the energy electron is increasing, meaning its delta E is positive. But here we're looking for the energy of the photon, but that's not going to require any additional math because whenever we do a transition in a hydrogen atom, the energy of the photon that is either absorbed or emitted is equal to the absolute value of our delta E. So even if we'd gotten the sign wrong here, we still get the right answer for photon energy, which is 4.48 times 10 to the minus 19 joules. Now the only trick here though is that's not how we're going to enter the answer. Here it wants us to determine the log of the answer, base 10, and enter it with 3 decimal places. Now there's no physical reason for doing that. The only reason we do that in some of these Blackboard questions, these are sort of relic questions that have been around for years, if not decades at this point. Basically, Blackboard doesn't handle exponential answers very well. It does better now, so you'll see some where you have to actually enter in the number in this way. But in general, if it's a large, especially a negative exponent, we'll just ask you to take the log of that and then enter the answer. So what we have to do then is take the log of this number, so make sure you know how to do logarithms on your calculator, because that could come up from time to time. Again, not in the math that we need to solve the question, but just in the math we need to report the answer in the correct format. So you have to know how to do that. Usually you just type the log key. It's not that hard to do, but in this case we would get minus 18, and then we want 3 decimal places, so it should be 315, and we'll have a little bit of leeway in the answer. So that would be how we would enter the answer. Again, the real answer for the energy of the photon is this number here, but it wants us to take the log of that and enter. So again, make sure you read the question carefully and follow all the directions, because for numerical questions in Blackboard, you do need to make sure you're putting your answer in the correct format or it won't count it. All right, now the next question is very similar, but this time it's looking for the frequency in hertz of the photon that will cause that same excitation. So a lot of the math is the same, but here instead of looking for the energy of the photon, we're looking for the frequency. But again, we're just going to use some simple relationships for photon energy that we will encounter at various times in this course. So we determined in the last problem, same n value, so we don't have to redo the math, that the energy of the photon was 4.48 times 10 to the minus 19 joules. And we know that the relationship between photon energy and frequency, which is what we're looking for, is going to be h times the frequency. So if we're going to solve for that, we're just going to take the energy of the photon and divide it by Planck's constant h. So that's the only additional math we have to do in this problem. If you were starting it from scratch, of course you'd have to calculate this number first, and then do this second step here to get energy converted to frequency. So it's going to be, again, 4.48 times 10 to the minus 19 joules. That's the number we calculated in the last problem where we asked for the energy of the photon. To get it in frequency, we just have to divide by Planck's constant. And so when we do that, let's get that. Alright, so what I got was 6.76. I gotta figure out the exponent. So I got 6.76 times 10 to the 14th hertz. So again, that would be the real answer for this question. But once again, it wants us, once we have the value, to determine its log and enter the answer in that way. So same story as the last problem. We need to take the log of this answer. Logs are always unitless. And so when we take the log of that, we should get 14 point something. We get 14.830. Alright, so that would be the correct way to enter the answer in this question. Again, the frequency is given above. That's the real answer, but just the format of the answer is shown there. Alright, so that's just one additional step from the last problem. We get the energy of the photon, and then we have to convert it into the corresponding frequency using this equation here. So other variations on this problem. Alright, so we have now, we're going to do three similar ones that all involve the wavelength of the photon. So usually we think of photons in terms of wavelength more often than frequency. So a lot of times you're going to be asked to calculate the wavelength, which again is just using the Bohr equation first to figure out the energy, and then a different equation to find. So here we have, what is the wavelength in nanometers of the photon emitted when an electron in a hydrogen atom drops from a 6p to a 1s orbital? Now, some of the confusion here might be, what do we do with these letters P and S? Because remember that those letters tell us the second quantum number L equals 1 for P, L equals 0 for S. So how does that factor into the Bohr equation? Well, the short answer is that it doesn't. So the Bohr equation, again, that same delta E equation that we're going to use in all these different types of problems, is only a function of n here. Alright, so for a one electron system like a hydrogen atom, we don't care what the value of L is. L has no effect on the energy if you only have one electron in your atom. Alright, so in this case, again, we only need the value of n. It doesn't matter that it's 6p and 1s. It could be, 6s, 6p, 6d, 6e, 6f, well, there's no 6e, 6f, 6g, and so on. whatever the L value is, all that matters for the Bohr equation is the value of n, which is going to be 6 and 1 in this case. So don't be thrown off by that. For a one electron system, we don't need to know the value of L to determine the energy. L has no effect on energy when there's only a single electron. So we're still going to use this equation. We're just going to put the n values in. We don't have to do anything with the different L values that we have. So the first thing we're going to do is we're going to calculate delta E using those n values. And this time we're going from a higher energy to a lower energy orbital. So it's going to be 1 over 1 squared. That's our final value of n is 1 for 1s. And then 6 is going to be the initial value of n for the 6p. All we need is the value of n in that equation. So when we calculate this, it ends up being a negative number because we're dropping in energy, and we get minus 2. I'll keep one extra significant figure here just to make sure we don't lose anything. Minus 2.119 times 10 to the minus 18 joules. That's delta E, which is negative in this case because we're going from higher energy to lower energy. What we're looking for is the wavelength of the photon emitted. So whenever delta E is negative, we're emitting a photon, and the energy of the emitted photon is just the absolute value of the delta E for the electron transition, which will just be the positive of that number, 2.119 times 10 to the minus 19 joules. So then once 18, I keep getting the exponents wrong, my bad. Alright, so then once we have this number, we just have to figure out, that's the energy of the photon right there, and again, we're looking for the wavelength. Energy of the photon is equal to h times c over lambda, so we're going to solve for lambda, which is energy divided by, hc divided by energy. Let's do my algebra correct here. And so we just have to plug the numbers in. 6.626. We actually used this equation earlier for the photoelectric effect. So we're going to put h, we're going to put c, and we're going to divide by the energy of the photon that we just found. And I did not specify the units in this problem, so I think we're going to just do it in meters. I believe it would have been specified in Blackboard. I just forgot to copy that part over. And so what I got for this was 9.381 times 10 to the minus 8th meters. So I don't know if we needed nanometers in this case or not. That would be 93.81 nanometers if we do it in the more standard unit, but either way, this is the math that's involved. So if we want to take this number to nanometers, we just multiply by 10 to the 9th. Alright, but again, it's another variation on the Bohr equation where we use the Bohr equation and then we convert to wavelength in this case instead of frequency. Now the next two are very similar, but they're just presented in different ways. So I just want to make sure that we're not confused by the presentation of the different questions. So here we're considering the following portion of the energy level diagram for hydrogen, and then it says, in the hydrogen spectrum, what is the wavelength of light associated with the n equals 2 to n equals 1 electron transition? So in this case, we have the energy values given, because remember the energy from the Bohr equation in absolute terms is just equal to that constant. Usually we use it in terms of delta E, but if it's just the energy value, it's just that constant divided by n squared, where n is the different energy values. Here we're just giving you the numbers, so we're in some sense saving you math. So there's again two ways you can do this question. We can actually use the delta E equation and basically ignore the given information, just use the equation that we know already and have been using for a lot of these problems. 1 over nf squared minus 1 over ni squared. Or if you want to make the math a little bit easier in this question, instead of using this equation, we're giving you the different energy values. So we're going from n equals 2 to n equals 1. So the delta E is just going to be the energy when n equals 2 minus the energy when n equals 1. And here, those numbers are given directly. Because remember, delta E means final minus initial. Actually, I think I actually did that wrong. should be n equals 1 to n minus to n equals 2, although the sign would just be what's changing anyway. Because we're going from 2 to 1, so we want to do final minus initial. So the final energy value is n equals 1, the initial energy value is n equals 2, so we could just put the numbers in that we're given. So that's going to be for n equals 1, that same Bohr constant, minus 2.178, just one significant figure additional. And then n equals 2 is minus 0.5445 times 10 to the minus 18. They're all given in 10 to the minus 18 order of magnitude. So we could just subtract the two numbers. We don't have to use this equation here, or we could just use the equation. You'll get the same answer either way. Alright, so let me get that number here in a second. Alright, so what we should get for this is, again, a negative number because we're going from a higher value to a lower value of n. And so we should get minus 1.6355 times 10 to the minus 18 joules. So that's delta E, just taking the two numbers and subtracting them. And again, it's negative in this case. And then we will just use the same set of steps we did before. So the energy of the photon is equal to the absolute value of delta E. And it's going to be 1.6355. I did not write that very well at all. Sorry. I'll learn how to write someday. Alright, so the energy of the photon is the absolute value of that. .6355 times 10 to the minus 18 joules. And then we're going to just, again, we're looking for a wavelength here. I didn't specify units, but lambda, using the same equation as before, is hc divided by E. And I'm not going to write out all the numbers, but it's the same set of steps we just did in the previous problem. So I'll give you the answer here just so you can follow along, but I'm not going to write all the steps again. So times 3 to the 8th, and then divided by that number. And what we should come up with is 1.22 times 10 to the minus 7 meters, or 122 nanometers. Alright, so that's how we would do that question. Again, we can use the information we're given to make our delta E calculation perhaps a little bit simpler, or we could have just gone with the equation and ignored the given information. The given information was meant to help us, but it wasn't necessary because we have the equation that we can always use. And then this next one here is, again, really the same type of question, just presented in a different way. So according to the Bohr model, the energy of the hydrogen atom is given by this equation. We gave you it in a sort of a non-standard form, minus 21.7 times 10 to the minus 19, but it's the same Bohr constant divided by n squared. Calculate the wavelength in meters of the photon emitted when the atom undergoes relaxation from the first excited state to the ground state. So this is the same math as the last one. The only difference is we have to make sure we interpret the words of the question correctly. So we're going to still use the Bohr equation, and here we're giving it to you in absolute form, but again, the delta E form is usually more useful, especially for problems like this where we're doing a transition between two energy levels. Alright, so this equation is going to get used a lot in this assignment. And the only difference here is we need to make sure that we're going to put in the correct values of n because we're not giving them to you in direct numeric form. So remember that ground state is the lowest energy state of any atom, in this case the hydrogen atom, and that means n equals 1 for hydrogen. So for one electron system, the ground state is n equals 1. And then here we say first excited state. So I'm not sure if I used this terminology in class, so it's possible that it caused a little bit of confusion. But an excited state is an energy level that's higher than n equals 1. So the first excited state, the first energy level that's higher than n equals 1 will be n equals 2. So when we say first excited state, that's n equals 2. second excited state would be n equals 3, and so on. So this is going to be the two n values we use. So that's going to be, we're going from the first excited state, so that's the initial value of n, to the ground state, so that's our final value of n. And so we're going to put the same numbers in, 2 and 1. So the math ends up being the same as the previous. We're going to get to the wavelength eventually, so I'm not going to go through that again. But again, it's just making sure that we read the problem correctly and understand how the words in the problem translate to the numbers that we need for this equation. So this one was same story, right? We're going from n equals 2 to n equals 1. Here we're going from n equals 2 to n equals 1 again. So it's the same number, so I'm not going to go through it again. But we had to make sure we could read the question to get those numbers out. Alright, the last couple of problems here deal with quantum numbers, which is the other major topic in this chapter that we covered in this assignment. So it wants to know how many electrons can be described by the quantum numbers n, l, m sub l. So n equals 3, l equals 3, m sub l equals minus 1. Now normally if we give you a set of quantum numbers n, l, and m sub l together, so a set of 3 quantum numbers, those 3 numbers together define an orbital. And as we know, an orbital can have 2 electrons maximum in it. So a lot of you probably picked the answer 2 in this case. But we have to first make sure that these set of quantum numbers are a valid set of quantum numbers. Whenever you're doing a problem like this, how many electrons can be described by these quantum numbers? There are some relationships, and if we're giving you 3 quantum numbers, then the most you could have with those 3 quantum numbers is 2 electrons because of Pauli exclusion. But we have to first make sure that the set of quantum numbers we're giving you is even valid. So n equals 3, that's a valid value of n because n can be 1, 2, 3, 4, and so on, any positive integer. So n equals 3 is fine. But if n equals 3, the allowed values of L are going to be 0 to n minus 1, which would be 0, 1, and 2 in this case. So when n equals 3, L cannot also be 3. That's an invalid second quantum number for this set of 3 quantum numbers. Alright, so for n equal to be equal to 3, L has to be either 0, 1, or 2. It cannot be 3, so that means there would be 0 electrons described by that set of quantum numbers. I did an example question in class that was very similar to that, where again, you need to first check if the set of quantum numbers we're giving you is valid. If it's an invalid set of quantum numbers, that means there will never be an electron that has that set of quantum numbers. M sub L is given, just to remind you, as minus L to 0, including 0 to plus L. In this case, minus 1 would be fine with that corresponding L value, but again, the L value is not allowed with that value of n. Okay, so n equals 3, L cannot also be 3, so there's no 0 electrons that would be described by those quantum numbers. So you have to make sure you check that first instead of just blindly using the equations that we have for number of electrons. So that's going to be the concept there. And then finally, the last one here is, with increasing value of the quantum number L, subshells are named S, P, D, F, G, H, I, so on. This one is not even really, that information is not really necessary for this question. That's just a little bit of background. But the key aspect of this is how many L equals 6 orbitals are allowed in a L equals 6 subshell. So again, we have some relationships for number of orbitals here. So we'll go through all of them. In a shell, which is given by an n value, the number of orbitals is n squared. In a subshell, which is given by an n and L value together, the number of orbitals is determined only by L. So in an L equals 6 subshell, no matter what the value of n is, the number of orbitals is just going to be given as 2L plus 1. So in this case, that's the relationship we're going to use. So we have L equals 6, and so there would be 13 orbitals in that subshell. So for a subshell, there's, a subshell is defined as an n and an L value together, but the number of orbitals in that subshell does not depend on n. So if L equals 6, whether n equaled 7, 8, 9, 10, whatever, the number of orbitals would just be given as 2L plus 1, which is 13 for any L equals 6 subshell. So that's number of orbitals, and then again the number of electrons would just be 2 times that. So 2n squared, that's maximum number of electrons in a shell, or 2 times 2L plus 1 for the maximum number of electrons in a subshell, because there's 2 electrons maximum per orbital. So there's 2 different related relationships that deal with number of orbitals or number of electrons in a shell or a subshell. Here we're looking for number of orbitals, and we're giving an L value, so we're going to use the 2L plus 1 equation. Alright, so that takes me to the end of this review. Hopefully that was helpful on some of these problems. There were many others that some of you might have had trouble with, so that's fine. Just get in touch with me on how to do those, and we'll get everything squared away, and we'll have, again, another assignment coming up this week that deals with a lot of related topics from the same chapter. Alright, have a good week, and I'll see you guys in class tomorrow.